Okay. So it's a pleasure today to introduce you, Teddy. The surname is Lapsnik. Okay. It comes from the Ariel University in Israel, but he's collaborating also with the University College of London. He got 2 PhD, one in mathematics and
computer science.
Okay, computer sciences. And we are collaborating for to apply artificial intelligence to the analysis of dog behavior. This is the reason why we start to collaborate and we meet each other. And now it's I think we thought that it could be a good idea to give this seminar to introduce also you to the possibility that artificial intelligence can in the future give us, in the present and in the future, give us in the analysis of animal behavior. So I don't want to bother you any longer. And please,
thank you very much.
Welcome.
So thank you everyone for having me here. Really exciting, and apologize for the slight delay. So today I would like to have a slightly unusual presentation. So usually in this kind of events, everybody comes and tell me about their research. I will do that as part of the rule for the game. But well, my objective for today is actually slightly different. I would like to show you as an outsider from most of your fields, what we can do as a collaboration from both sides. So your applied sciences and more like the traditional, well, not traditional, but like the computational side, so mathematics and computer science. And I will present today 3 papers, if it will work. Wonderful. So I will present 3 papers. And while the papers themselves can be interesting, I think the main point that I want to convey for you today is to what we have done in the studies, which combines real-world questions and data and like computational methods, like advanced computational methods. And the idea is to show you different ideas so you can think about what you can do with this kind of methodology on collaborations with other colleagues. So without further ado, the motivation for exploiting AI in animal behavior analysis. So first of all, increasing complexity in behavioral studies. In a lot of behavioral studies, at least from what I see, again, as an outsider, take any claim that I provide today as an outsider, it's important. There are a lot of statistical analysis, classical one, linear regression, logistic regression, which is amazing, don't get me wrong here, but it doesn't provide the full potential that you have with your data. I saw with my colleagues how hard it is to collect the data that you have and how frustrating it can be. And then you get in a lot of data, quality one, and then you don't fully utilize it with more advanced stuff. So AI and machine learning and advanced mathematics can be really useful in that. And my claim is not that you need to do that, but you need to find someone to do it for you. We'll be happy to do this one. Enhance accuracy and precision. A lot of times as a reviewer myself and from colleagues, I hear a lot that, okay, and 75% accuracy is good enough for publication, 80% accuracy is good enough, 85. So some people will say, okay, 75 is great. Others will say, oh no, less than 90% accuracy, I don't publish it, like something like that. And the fact that a lot of time we can actually scratch more percentage out of your question or data by reversing the problem or define it slightly different. And it's not harming in any way the biological animal behavior question in the research, but it's proposing it computationally slightly different, and you get in better results without p-hacking and stuff, really against p-hacking. And unleashing new insights. So interestingly enough, when we actually solving a problem, for at least from my personal experience with colleagues, people come in with some question and relevant one for the research, and they usually don't notice a lot of like secondary, which can be interesting as well, questions that can emerge from the data. I give an example in the slide next few slides, but just an idea, when you're solving a real world question, sometimes you actually can solve in addition as a secondary or third level questions and other computational or secondary real world questions. So without further ado again, the first study is social function of domestic cats facial signaling. So every presentation becomes more cute when you have cats in the presentation. It's a well-known fact. So here are my cats. And the idea is as follows. We as humans have facial signaling. It's a well-known studies, micro signaling, macro signaling, a lot of them. The question is if our cats have them. And the answer is yes. And more interestingly than yes is how we do it exactly. So cats cannot say us if they have the facial signaling. And if you ask experts, human experts, they don't do a really good job, unfortunately. So what we can do, we have a cat, as you can see here, and we actually find 48 points on the cat. In order to do that, we have developed, me and my colleagues developed a deep learning computer vision algorithm. We gave it, I think, around 6,000 images of a cat, and someone manually put the points. So the points are well defined according to some scheme. And we trained the model to recognize, given a new cat image, to find these 48 points. So the 48 points actually make us a representation space we can use because it's numerical. So my work as a mathematician is taking your request, for example, an image of a cat, and convert it to something which can be represented by a vector of numbers. Once we're in the vector of numbers area, I'm feeling comfortable. Before that, it's a mess for me. So this conversion is an important point. So now when we have the points, we're using some augmentation, rotation, just to make it like the picture clear, and we get all the points. Now when we have the points, we can do two things. A, we can associate a distance, so a sequence of these points, so basically a mimic over time, with some signal. So you can see here AU25, AU26 as indexes of some social signatures that we have in mammals. And the question is cats actually reflect like mimicking something they see? So you can see here, for example, there are a sequence. You have two cats, the signaler and the recipient, okay? And the signaler making spontaneously signal AU25, AU26, EAD 102, etc. And you can see it's happening over time, of course, signals. And the question is the receiver actually reply with same or different signals? Again, the ability to do that from a video, if you try to do it manually, it will take you like ages. But once we train the model, it just running through the model, and the model takes the video, sequence it in images, get from each image, recognize who is the signaler, who is the recipient, which is a task by itself, so you skip it for now, and getting the right impressions and putting them on the timeline. And what you can see here, for example, you can see that AU25 is matched, this matched, this is not matched, this is matched. So intuitively, we can say that 75% from some windows of time is matched, which is, well, mimicking a response. Again, we like to quantify stuff with equations. So my PhD advisor told me that every presentation, that every slide that have equations, you lose half of the audience. So I lost all of you. Okay, so as you can see above, this is so here, I don't see my mouse, never mind. So above you can see the sequence. So S is the signaler, R is the responder, and the time frame it happened, and the signal itself. So this is the example from the previous slide, from this one. And we have two metric sets. We have the metric arm size, which basically saying how much similarity between the signals in a time frame, and RM ratio saying what is a different metric, which says, okay, is there another signals which wasn't part of the mimicking process? So using both of these terms, we can actually get a good experience from how well the mimicking was. And as you can see in the results, So a lot of videos have a low percentage of frames which detected cat faces. So this is an issue, right? So if I claim that I want to calculate that, I need to be sure that I'm finding the signals well. And actually, we're doing for some data sets a good job. And for some data sets or some tasks, we're doing a worse job. This is a task. If you actually will see the videos, and you're probably familiar with these kind of videos, the cat doesn't look on the camera, they move away, they have blurred, etc. So we wanted to profile how well is the pre-processing step is happening. Assuming you're okay with this slide, we wanted to understand how we recognize the faces. So I told you that we use these points to get the signals, right? I never explained you why. So now let me fix it. So we're actually interested in a lot of parameters. So we computed these features. And the features actually looking on subsets of the images I showed you before, this slide. So they look on this combination of subsets of these points and try to understand what the model used in order to map between the points, the 48 points, and the signals that we are seeing. So you have a lot of features which I won't explain in the moment, but the interesting part is you can see it's really diverse, which is important for us, because if it was like one line really like high, for I don't know, 50% of the confidence of the model was on a single feature, it will be problematic and unrealistic. So this distribution makes us happy. And just to make it more like clear how it looks like, so you can see a single EADU 104, it's a movement of the ears. So you can see in the space I'm feeling comfortable with how it looks like. So the cat starts with the red points. In the middle of the signal is the green points, and the endpoint in the blue signal. So you can see here not a lot of the movement, right? But here you can see really large movements on the ears, which makes sense because it's ear movement. So just to give you an idea how it looks like. So we tried a lot of algorithms to make sure that's how well it's happening. I think this slide is really important to show you what a good like machine learning and data science can bring you. If you go on the standard stuff, I don't know, reinforcement learning, random forest, which is like standard nowadays, you get good results, but it's still like below 60%. But if you actually pull out all the big guns and try really hard, you can get up to like temporal KNN gets you up to almost 75% accuracy on the same task. So I think the slide is important. Any question up to this point? Wonderful. So we, as I said before, we have the two matrices, and again, statistics is important. We don't forget about statistics. So we wanted to see in affiliative and non-affiliative social conditions if we see any difference. So you can see the answer is yes, basically. This is as much as I can say as a mathematician on this slide. Here's some kind of like what the main sequences of signals they can see. This is really nice because it will take you a long hours to do it manually, and the algorithm can do it in like less than a minute. So it's really nice. Well, it's similar to the previous slide. I can skip it quickly. No questions at the point. Wonderful. So this is the first study. Without letting you to rest even a second, let's jump to the second example. So again, cats, really nice. And here we take a slightly different angle about cats. Similar input, we have videos like before, but now we want to detect pain in cats. Okay, so again, how we done it, we have a video, we take the frame sampling, we find the face of the cat, not an easy task by itself, as you saw before. And from this image, the cropped image, we find the 48 landmarks. Yes, same model as before. I really invested in this model, so we use it a lot now. So we have the landmark detection, and we have the vectors that I described a few slides ago. And now the cool stuff. once we have the landmarks, we try to find pain. So it's somewhat similar to the signaling from before, but now we actually need to take this data and we say, because we have like pain or no pain videos. So the tagging was not on a single frame or a sequence of frame, but on the entire video. On over a video of like 40 seconds, the cat doesn't have like consistent pain. It's really hard to use. So we need to take a really like poorly made tagging and use it to extract pain. So this is like the computational challenge. Our approach was as follows. So we taken the data, which is again, is a lot of data. So think about it. We have 96 numbers per frame, 30 frames a second, 30 seconds. So like thousands of numbers and a single point, like pain, no pain. So yes or no. So it's really uncomfortable computationally to look on this dimension. It's really large, it's really sparse, not really easy to use. So we took this data and put it in something we call autoencoder. So a deep learning architecture, which takes the large space and compress it into a smaller one. If it sounds like a Chinese, it's fine. So the main idea is big, messy computational space, small, really appealing computational space using black magic. In other conferences, I cannot say black magic, so I'm really happy to be here. So this is the first thing. And with the a nice representation, we actually solving a time series question. We have a sequence of frames, which is the computationally appealing space, and we try to find the pattern, the temporal pattern. Okay, so notice in here from this part to this part, we're speaking about spatially components, spatially properties, because it's the location in space, right? And here we're actually solving a temporal problem. So we get in a really special temporal model. So we train this model to detect where it's pain or not using XGBoost, some algorithm, and we get in a prediction from the model. Yes.
Can I interrupt?
Yeah, sure.
Question. So, since you are training the model, right? How do you tell the model that is actually pain, or is the model that learns by itself based on changes? Let's say, half a second ago, the points were in a specific position. Now they are in a slightly different position, then in a slightly different position. So how does the computer or whatever model knows that not that something is changing, but that is actually pain?
Oh, it's a good question. So the answer is someone tell you, you have a video, and a human expert tells, here's our pain.
You need someone obviously
yes, for the training.
That frame is a frame of a cat in pain, and so the computer, the algorithm now
yes
try to recognize those patterns.
Yes, specifically for this study, because people again not really sure when pain has cat has pain. Specifically here, if I recall correctly, we used videos of cats after operation. Like right after operation, which is known from the literature that are in some level of pain. Again, it's really in the study I've shown in a few slides, and the distribution was really unclear because you don't know if they're in slightly pain, a lot of pain. You just like assume they're in pain, and the distribution is better. So if the tagging was better, the model was better. But like working with whatever we have.
I guess that it can learn just that there is a little bit of pain there. It can then probably learn better to recognize when the pain is even.
Yes, if we have
someone telling him that he's in strong pain, I guess.
Yes, we didn't do it, but hypothetically, yes. So this is how it works. Basically, don't get afraid from all the figures. The idea is as follows. Again, we're trying to get in a easy to use computational space, convert it into something which is nice to use. And once we have this nice to use space, we actually try to predict temporal information. So as a common theme in this kind of tasks, that we get in a really easy to understand, but not really easy to use computational space. We do some magic to make it easy to use or more easy to use, and then solving some case of a regression problem, classification, or time series, one of three. So this is this idea. So as I promised, so again, has three tasks. So face detection, we have two different data sets. We wanted to make sure this is robust technique. So two different data sets from two different studies. Face detection. So you can see Finke is really have good images. It's really easy to find the faces, but Ticho is really hard. Just for some context, Finke is like a well-studied, with a fixed camera, everything is really fixed, everything is really laboratory style. And Ticho is more like internet images, so everything is a mess, but Ticho is much larger. So this is the trade-off. So you can see the face detection is slightly worse here. It's consistent here in the landmarks detection, because we find the faces really well, we find the landmarks on the faces really well, but here it's all over the place, by chance more or less. But the pain detection, we was actually relatively good at that. So these numbers of confidence is really low, but the performance is fine. So the interesting, this is what I'm saying about the pain profiling, because the target of the pain wasn't really precise, the confidence of the model was low all the time, even the model was actually relatively well. So it's a good point. The model can be working well, but still not confident about itself. How well? So for Finke, the best one, for not the best one, but the simple one was around 70-something% accuracy. And you can see a drop in the automated one. So here the manual tagging of the faces, here is automatic. So of course it's worse. We also wanted to know about the video. So video is coming, you can sample it in different FPS, frames per second. So as you can see here, if we actually increase the number of frames per second, rather than the model more data, basically, we actually getting better results. The interesting fact is that after 6, which is not presented in this table, you don't gain much more experience. So it's plateau around 6 frames per second, which is actually good news because we don't need to sample 30 or 60 frames per second, as usually people do with video cameras. You can sample much less. And it's amazing because less storage, less traffic on the internet, like it's easier to work with. So keep it in mind. And here we actually tested for different window sizes of frames. So again, you can see some improvement as we take into more temporal data into consideration, but again, plateauing really quickly. So the interesting fact that if we plateauing about 5, 7 here and here or 5, and we use this, so the pain signals are the outcome of these two tables is the pain signal is more or less a second long, even less. So it's outcome that we get from understanding how the model performing, and we learn something about the real world data, which I find interesting. Next. So when we consider the 3 frames per second, this is the model's performance on the entire pipeline. So the accuracy is around 68%, 65 for Ticho. Well, not amazing, right? Like 0.9 usually for this kind of stuff. But for the first paper, we was happy to get it. When you profile for each data set, the importance the model provides to the frame. So again, when you signal a signal, it's over time. So you need to give some weight to each frame. You can see that both data sets, the middle frame, the center of the pain signal, if you want, getting the most, but it's actually getting also really weighted across both sides. So we can learn that the signal of the pain is more or less symmetric around the middle. Not sure what to do with it. I hope you have an idea. But another interesting outcome. Any questions so far? Wonderful. It's either I'm an amazing speaker or you don't care. One of them. So the last one, just to keep you in good shape, vocalize and analyze of dairy cattle. So no more cute cats for you guys, sorry. Cows this time. So cows actually, they produce in 2 types of calls, high frequency, HF, and low frequency, LF, which associated with pain and no pain again, or good vibes and bad vibes. So we actually collected data about cats in dairy farms. And you can see an example of the audio signal of one cat, of one cow. So this is over time, so 8 seconds or 8 seconds signal, and this is the frequency of the signal, and same here. So you can see the high frequency is really like all over the place, is really chaotic, and the low one is like more spread out and like smaller frequency. So when you look on this kind of stuff, again, I don't feel comfortable with because it's not a vector of numbers. So let's make it a vector of numbers, as easy as it sounds. So we look on the previous image and we proposed, well, this is not our stuff, actually other people proposed this set of features before us, and we adapted. So you can see a lot of features. Actually, most of them are not one feature, but it's repeating on different scales. So for example, the FO mean of mean frequency value equals the core, so equals what core. So you can define different window sets, different thresholds. So each feature here is like meta feature, and you can define sub features out of it. But just to give you an idea of the feature space we used. So we wanted to make a simple classification task. Give me a call. I tell you if it's high or low. That's it. This is the first step, or the last step, actually. If you want to make it in a real production model, you should actually ask a really pre-processed question, which is when I see the call, right? Imagine you have a microphone in the farm and you just like quiet, or like birds, woods, I don't know, some sounds, and then the cow makes a signal. So you need to detect that the signal started. We don't do it here, but it's a question you should keep in mind. But once you notice the signal and capture it, you want to understand if it's high or low. So now we can use the classifier. So the results you can see here are across a 5 cross validation, just to make sure the results are robust. And we try 2 different approaches. The first one, given the signal to a deep learning model, which importantly need to say is unexplainable. We don't understand why it does it, what it does. We don't understand why it makes some prediction over other. We don't know anything. It's a black box. You just give it the data, train it, and hope for the best. And you can see it's actually quite good, like 90-something% accuracy. On the text, it's slightly less than 90%. And in the explainable model, which is, well, by its name, we can slightly explain it, it's worse. I would like to take a second on this slide, just saying this is not a fluke or an anomaly, it's a pattern. In all the studies, when there a trade-off between how well the model performs and how explainable it is. So it's always a trade-off. When you ask for the best model, you usually will get the black box one, nowadays at least. And if you say, okay, but I want to understand something, you pay with accuracy or the performance of the model. So more complex models performing better, but be less able to explain it. So there's some like imaginary line between the two, explainability and performance, and you need to decide in each study where you want to be. In some studies, you say, I don't care, I just want it is a technical part. I want it to be as accurate as I can. So no explainability. And if the model is the main subject of the paper, it usually should be explainable. I'm doing a lot of medical research, so which like MDs, and they don't agree to anything unexplainable. They want to understand what's happening because they may give the drug to a patient. They need to understand what's happening, and they're paying with accuracy and performance. So it was an important point. Next slide, you actually see when you actually take for each one of the subject separately. So if we want to find an individual model for each cow, I don't know why, but let's say you was able to identify a cow and you want to say what its condition over time. So for each individual cow, we was able to low frequency, high frequency, and both get the following results. Okay. And as you can see here, on like in comparison to this slide, which is like I showed you really promising accuracy, here I actually have less promising one. And the explanation is we don't have enough data. Okay, when we have a lot of cows and we have a lot of data to train the model was able to gather patterns. But here we have one cow. I don't recall the exact numbers, but it's like almost 2 orders of magnitude less amount of data. It's a lot. So if you have more data on the cow, those numbers will be more similar to this slide. But unfortunately, you lose a lot for small, like individual stuff. And actually, we see it in any kind of study, which we take a population and we divide it to a personal models for each one. You see the same pattern. Okay, so if you have like 8 dogs and you want the model for the entire population, it will be better than each dog individually. Okay. And again, as you can see, as I promised you, the DL and expandable should be on the opposite. So here it's happening, here it's not, etc. And the reason it's not happening, as I just said in the slide before, as you can see here as a good example, is because there are not enough data. So DL is more data hungry. It's not like it's losing the competition, it doesn't converge to its full potential due to the lack of data. Wonderful. Do you have energy for last one, short one? Wonderful. So last example, I promise you, it's came out for. So we have dogs, because dogs are great. And we wanted to find when dogs has problem breathing. So there are breeds of dogs that have like a small nose, and they have, I can show you this guy. I don't recall his academic name, scientific name. Let's call him the dog with the short nose, lacking any more proficient naming. So the challenge is to understand when they have a breathing problem, and we actually can do it again with audio. So we do the following: we connect the data about the dogs. We get the signals, similar for the cows, more or less the same kind of data. We process it to a vector of numbers. Yes, it's repeating itself, I know. And now we actually tried really unique algorithms. So we developed a really unique one. It's a combination of 3 algorithms, well known, but the combination is new, which we find exciting. This is the prediction model, and we make a statistical analysis. So how we train this model? We had 69 packs. Packs the name. So we have 69 packs and 79 non-packs for this conversation. And we recorded 15 minutes of the breathing, but it's important during a workout. So they need to get air. So we recorded all the dogs, and we have post-exercise sample after 5 minutes, 10 minutes, and 15 minutes. Okay, so they becoming tired over time. We extracted, as you can see, 6,373 features, just to feel that we have enough. So we have a lot of features, again, in the similar way as before, so something like a subset of these features. And we use the ensemble model that you see in front of you and the results. So the accuracy of the prediction for packs, when it's trained on only the packs and tested only on packs, you can see like 0.678, 0.68. When it's on everyone and tested on everyone on rest, is 65, etc. But we wasn't sure if these results are because we're doing something wrong or the data is hard or something like that, because let's be honest, 68% accuracy is not amazing. So we actually tried another question. As I said you before, we started with this research question, but they said, interesting if you can say something else. And we actually tried to find laryngeal sounds. And here, as you can see, we're doing really well. And this is the same model. So probably model is not a problem. So we try to understand what is happening. And if you can notice, here the segment was rest. In rest, they don't breathe much. So not much signal. And what's happening is once we introduce a condition, so you can see packs and packs, and after 5 minutes, 10 minutes, 15, and all the combinations, you can see that once we have all the data, like all 3 samples of 5, 10, 15 minutes, we actually get into 85% accuracy, which is again already more corresponding what we see on the secondary equation. So here you can see that actually we get a lot of stuff. And finally enough, after just 5 minutes, as you can see in the first row, we get almost the same accuracy. So just the fact that we introduce something actually allowed us to improve the results. Here, just for comparison, just the 15 minutes on different configurations doesn't change much, which makes sense. Any questions for this point?
Why do you think that 10 minutes is so lower compared to?
The 10 minutes, I don't know. Maybe after 10 minutes, I have some kind of non-linear effect. So just a summary slide. This was quick. So help the math/AI colleague to help you. Unusual slide. So 3 points for me. Question definition. So you have your research question definition, which is appropriate to each of your respected fields. But when you want to work with the math/AI colleague, we need you to define it as follows. We need you to define what do we know, yes? And define it not like, yeah, cats are cute. No, cats are numbers, right? So cats have a property which is a number. So we need to know it as a numerical values. What do we want to know? Why? Again, you will find it funny to hear, but it's really non-trivial to answer it computationally what we want to know. We actually had the discussion yesterday with another colleagues, and the question of what we want to know was like 30 minutes talk just to understand what we want to know. Sounds so trivial, but not really. So what we want to know, again, numbers. I know it's frustrating for sometimes, but we need numbers. And the most important is what is may influence it that we don't know consider, right? So sometimes you have, most of the time, let's be honest, you have something in your head, you have a lot of them, and we don't. Like, I don't know X, Y, Z, and you find it so trivial, you don't even mention it. And then it's really frustrating because when you do the analysis, you say, something happening and I don't know why. And if you just control for some stuff that you know, everything makes sense. So I think the dogs example from before was really pointing to this part, because once you understand the data is underrepresented, it was able to really easy to solve the problem, because up to this point we actually struggled a lot with the modeling part, which was unnecessary. So this is the question definition. I will repeat it just for case. What do we know? What do we want to find? And what control, basically, what may influence it and we do not consider. Okay, assumption of the model, assumptions that you have, etc. Data collection. So really my request to you, speak with us before the experiments. Please do before, not after. Yeah, it's fine if you do it after, but it will be harder for, at least for me. If you do it after, we are not able to define something. So maybe you collecting data for your question, and we just, by the way, if you collect this and this, I can use it later for some kind of analysis. You find it, okay, who needs it? But we actually do find it really easy to use. So involve us in the experiment preparation. We don't usually contribute much to the how to do the experiment. Usually like, yes, collect this data for me. Not much influence on your part. And the last point is the analysis request. So when you ask for some kind of analysis, again, the desired outcome in a numerical manner, and specify exactly what is the data can be used for the analysis and which cannot. I have a really short funny story about that. I worked with clinicians from the UK, and they give me an Excel of data and drug performance that I needed to predict. So given a patient, how well a drug will work on the patient for a given condition. And I trained the model on all the Excel because I assumed I can use it. My mistake, apparently. So I use the data and we get like 95% accuracy. And I'm working on clinical data for a long time now. 90% is unrealistic. Like maybe I'm good, but not that good. So I came back and said, something seems wrong here. And when I said it, if I didn't say it, the medical doctors wouldn't like, 95, great, let's publish in Lancet. So no, it's something wrong. And indeed, I actually used the parameter which is only available after the treatment, which is highly known to be correlated to the outcome. And when we actually profile the importance of the model, we find the model to use it like 90%. Yeah, I told you like this Give me a second. This slide is really great because it's actually distributed well. So we have like really long one and another 10% like all over the place. So I will get back to the point I wanted. So tell us what we cannot use. Please do, because it's really, really frustrating to do something and try and find out that, of course you cannot use it. So when I told it to the clinician, I said, I'm not a doctor, like not the right one, and the mathematician one. And I didn't know that. I don't know the literature. So we fixed it, everything is fine. We didn't publish in Lancet, you know, the cool story. So be sure to know that and be sure to specify any assumption you use in the data collection process. It is super important. This is not the same as what question of data, but assumption in the data collection. So I will give you another short, really cute story. People try to train a model for automatic cars. So a really known story from Google. And they trained the data really well on Miami, sunny Miami. And at night and days, they try to get as quality data as they can and deployed it in Alaska for tests because I have a test facility in Alaska. And the model crushed the car into a wall like in 30 seconds. And when they tried out, they find a really interesting point. Miami don't have snow. Shock, I know, but this is happening. And the model just like see all this white, get confused because this is the first time in his life in production seeing white, snow, and you just crashed the wall because it wasn't able to get any decision right. So let us know the assumptions. What's collected data? So if it's in a specific lightning, if it's a specific condition, if it's specific farm, specific something, all the specifics, it's fine. Let us know. This is all the request. We can take it into consideration. So your car won't crash into the wall. It will be safely riding to success. This was me. Always looking for exciting collaboration and research projects. If you have any idea, feel free to email me. This is my personal email. This is my website. So summary, take home, and picture. Thank you very much. Any questions from the audience?
Yes, a little question. Can you go back one slide because I forgot actually. So in the first suggestion, right? You'd say to define research question in data, collecting data. Are you talking like, say, I come to you, I have a research in mind, I want to collect data. So basically, I should come to you with some kind of equation in my mind, like what do you mean for presenting with a data perspective with numbers?
Yeah. It's a good question. So no, I don't expect any equation from you. This is my work. Let's keep it like that.
But clear what is the dependent variable, the dependent variable, the covariates, and all that kind of stuff. Basically, that is.
Yeah. So basically, if you say this is dependent, and you can say either this is a continuous variable, this is a categorical, this is ordinal, even just like a scheme of what you get and what you want to find.
Which somehow is like a statistical equation, more. But more and more in
even without the model, just like that. So for example, if you're using like classical statistics, the assumptions you use to pick the model is good enough. Like
okay.
Yeah, because if it's a continuous variable, so if you want to predict something continuous or discrete, is really different from me. So discrete prediction and continuous prediction, like changing the entire way how I treat each task, if it's time series, non-time series. So again, it's not just coming, it's never like, it may sound like you're sending an email and waiting for like a magical response. It's a ping pong. You send an email, you get an email. If you work with me, you get a lot of emails. You can ask Paula, too many of them actually. So it's a ping pong sort of. But yeah, you need to define what you know numerically and what you want to get numerically, and we should be fine from there. Any more questions? Yes.
I have a question about imputation. So the ability of impute a movement using something that's happening in other parts of the face. So I'm wondering, for example, moving the ears to be associated, it's linked to something else. So if you explore that, if you use that, if it's possible to do that.
Yes, yes, and yes. So again, we don't want it to provide too many stuff, but here we actually do something like that. You can see different pairs of signaling, and you can see the movement between them. and actually reach the features, this list of features, we actually can do exactly that. We can impute a part, like if you say, for example, only the upper face, we can impute the lower face and the opposite. Not perfectly, of course, but relatively well. We actually done something like that, and the result was between 80 to 90%. Don't get me on the number, but it was relatively well. And again, it's usually this kind of projects, at least for me, if I get like 10 times more data, I know it's really hard for you, this statement, but 10 times more data, usually the performance can improve much significantly. We usually work with a relatively small amount of data. So if you can make it larger, it usually helps.
What is more than this?
It's really depend on the question. So 6,000 6,000 cat images provided a really strong deep learning model. So 6,000 is amazing, but as you saw before, we have like data from 70 dogs, which already provide like 0.85. But if you ask me if you get like 700 dogs, it will be better, of course. But like we don't have any magic number when it's good enough. It's usually what I recommend to do is take a small sample, and when I have the small sample, I can make some prediction of what is the sample which get us to some point. It's a good point to say actually that if some of you using power test, don't do it. It's not working, it's never worked, and the assumption to make it work is not correct. I would love to expand on this if you want. Yeah, I have a full lecture just saying how bad power tests are. Really don't like them, and you should not as well.
It's interesting because literally every journal where I had to publish, they just, the last 10 years, right? They ask for power analysis.
Yeah.
Right?
Yeah.
And they just hit your head.
Yeah.
Before the experiment or after you done the experiment?
No, before.
Okay, so but before it's
Actually, you're
just
talking about the post.
yeah, the post is easy because you know that. So the post is post-mortem. The patient is already dead. But the before, just like in 30 seconds, because I don't want to spend too much of your time. So when you do a power test, you have an assumption on the data distribution that you should get. But how come you know this assumption is true? And usually like 95% of the time, will be super surprised if you say otherwise. You assume it's normally distributed, which is fine. I like normal distribution like the next guy, but it's usually not the case. And even if it's similar to normal, it's always has some, especially in your fields, like animals are, I really like how Paulo said it, animals aren't predicted. So even the somewhat normal, it's not really normal. So you need to have like in the power test, the confidence, and then how you measure the confidence level, and so on, et cetera. So as a mathematician, I don't find it sufficient or meaningful to make power test because the assumptions of the computation of the power test is invalid. So I don't believe any number in the other side of the way because the input is not true, or you don't know this is true. So how you can make any claim?
Still, it can be an intelligent guess, right?
Okay. I like intelligent guess. 50.
Just to start from the sun. Yeah.
Yeah, I really like the claim. You're not the first one to do it. I really like it. So everybody that asks me for intelligent guess, I have like one number for them, like 50. As mathematically speaking, my guess and yours are like identically probability. So you can say any number that you want is like statistically speaking, identically probable. So yeah, I'm making a joke, but yeah, I totally agree with you.
It's very interesting, actually.
Well, thank you very much, everyone, again.